Okay, so starting from today, we're going to talk about some algorithms. On our list, there are backtracking, divide and conquer, dynamic programming, and greedy algorithms. And these are the classical ones. Then we'll take a look at the concept NP. We'll see what that is. Basically, it's a way to tell how hard a problem is. Um, then we're going to continue talking about some algorithms for solving the hard problems. We'll discuss approximation, local search, and randomized algorithms. And finally, to get you prepared for dealing with the big data problems, we'll check out parallel computing and external sorting. Now, let's start from backtracking. So the first thing is always to understand the reason behind an algorithm. We say that a surefire way to find the answer to a problem is to make a list of all candidate answers, examine each, and following the examination of all or some of the candidates, declare the identified answer. That is called the exhaustive search. In Chinese, we say it's 暴力枚举，暴力枚举的算法。If we do so, then we can guarantee that the answer is indeed correct because we have tried out all the possibilities. But, say sure, since it's a surefire way, if the list is finite and it's possible to identify the answer following the examinations, what does it mean? So what if there are infinitely many candidates? That will be really complicated. Okay, and we'll see later. For the moment, let's just assume that we do have finite number of candidates. Another problem is and if there are not too many candidates. So what if the number of candidates is like exponential? Or say even worse, what if it's a factorial, right? Then we won't be able to find the answer in our lifetime. So backtracking is a kind of smart searching. Okay, it's a kind of smart searching that can eliminate the explicit examination of a large subset of the candidates while still guaranteeing that the answer will be found if the algorithm is run to termination. This kind of elimination is called pruning. In Chinese, we say it's 减枝搜索, searching with pruning. So basically, it's like we're searching in a solution tree. Exhaustive search means we must check every node in the tree. With backtracking, we can tell at some early stage that some branch is impossible. So we don't have to continue along that way. And therefore, we cut the whole branch of a subtree and therefore save some time. So the basic idea is to solve the problem step by step and to form a complete solution by adding one piece of the solution at a time. So suppose that we have already collected I pieces at the moment. So we have this partial solution consists of from x sub 1 to x sub I. And then to obtain the next x sub I plus 1, first we check that by adding that x sub I plus 1 to the partial solution if this one satisfies the constraints. If everything's okay, if the answer is yes, we continue to add the next x sub I plus 2. Okay, and if we have tested all the possible x sub I plus 1s, yet still cannot find one that fits, then it means that this x sub I doesn't work. So we're going to delete this x sub I and backtrack to the previous partial solution. Well, it still sounds quite abstract, right? Let's study some examples. The first example is the famous 8 queens problem. We're supposed to find a placement of 8 queens on an 8 by 8 chessboard such that no 2 queens attack. Attack means, we say 2 queens are set to attack if and only if they are in the same row, same column, same diagonal or anti-diagonal of the chessboard. So here comes your first discussion for today. Please draw 2 different solutions. Here, well, if 2 solutions are symmetric, they are considered to be the same solution. So you're supposed to draw 2 different solutions. Okay, now I suggest you to pause here and see how long it's going to take you. Lot of solutions, right? Here I'm just showing 3 of them. So have you tried? Can you see the pattern? I mean, if you're asked to write a program to find the solution, what would you do? Now let's see how it's solved by backtracking. So first of all, how is the solution represented? Although it looks like a 2-dimensional problem, I mean the chessboard looks like a 2-dimensional array, right? But with some constraints, we can simplify it. See, let's denote the queen in the ith row by q sub I. And since they must not be placed in the same row, we only have 1 queen in each row. So this is unique for each row. That means we only have to record their column numbers, right? Now, let's denote the column index of q sub I by x sub I. And therefore, a solution can be represented by what? By a sequence of x sub i's, right? So each position, the ith position corresponds to the ith queen in the ith row. And the value of this x corresponds to the column number of that queen. So for example, a solution like this can be written like this. So what does it mean? So the first number is 4, means the first queen, which means the queen in the first row must be placed in the 4th column. All right. The next number is 6, means the queen in the next row must be placed at the column number 6, and so on and so forth. So basically, we're going to solve this problem step by step. And at each step, we're supposed to determine the proper column for a queen. And the constraints are the following. Well, this is the space for each x, which means that each x can pick up a value in this range, right? It implies that there are 8 to the power 8 candidates in the solution space. Why is it so? Because there are altogether 8 x, right? Each x has 8 possible values. So altogether, we have 8 to the power 8 possible candidates. So in general, if it's an n by n problem, there are going to be what? N to the power n candidates, which is really horrible. It's even worse than n factorial, right? N to the power n is much bigger than n factorial. But fortunately, we have more constraints. Like this. We have made use of one constraint that they must not be placed in the same row. And there's another. They must not be placed in the same column, which means if I is not equal to j, then their column indices x sub I and x sub j must not be equal. So this implies that the space is reduced to 8 factorial. It means that the solution must be a permutation of the numbers from 1 to 8. So for example, if the first queen occupies the fourth column, then the rest of the queens will only have 7 possible places to go. 4 is no longer included, right? Once we place the next queen in this column, then the rest of the queens will only have like 6 options, and so on and so forth. And therefore, this is no longer 8 to the power 8. This is actually 8 factorial. So in general, if this is not 8 by 8, but n by n, that will be n factorial. Still quite bad, but much better than n to the power n at least. And also, they must not be placed in diagonal or anti-diagonal, which means this condition must be satisfied. So for the problem with n queens, there are n factorial candidates in the solution space, which means if we do exhaustive search to try out all the possibilities, this is the total number of possible candidates we must check. Now let's go through a 4-queen problem manually to see what backtracking does. We only study 4 queens because I don't have a very large screen for the 8 queens. Alright, so step 1, what we do is we must construct a game tree. So this is the game tree corresponding to the 4-queen problem. So we start from the root. The first thing to do is to find the place for the first queen, right? And therefore, on the first level, x1 has 4 options corresponding to the 4 branches. And the second level corresponds to the second queen. Once the first queen is placed, 1 column is occupied. And therefore, the second queen will only have 3 options, right? For example, if we search along this path, it means that the first queen is placed at the column number 3. Then for the next queen, there are only 3 columns left. 3 is not included. Alright? So similarly, the third queen will only have 2 options, and the last queen will only have 1 position left. So a path from the root to a leaf node corresponds to a candidate solution. And there are how many different paths? The same number of leaf nodes, right? So in this case, there's going to be 4 factorial leaves, right? And each path from the root to a leaf defines an element of the solution space, a possible, a candidate answer. Well, of course, not all of them are real solutions that satisfy all the constraints, and we're supposed to check them out to find one that works. Okay, so step 2 is to do a DFS, depth first search, which is a post-order traversal of this game tree, which means we must first confirm its children's status and then decide if this node works or not. Okay, notice that these numbers correspond to the order of checking. Now let's start from the root. So at the very beginning, I colored this node as a green node, means it's alive. It's alive means we still have several directions to go. So this node is still alive. Now let's move along the first branch, which means we place the first queen in the first column. So x of 1 equals 1. And we are here. The second node is also green because we have possible ways to go. Okay, now let's move along this path. It means that x2 is 2. We are placing the next queen in the second column. And we check the constraints. They belong to the same diagonal, so that violates the rule. And therefore, it means that this position doesn't work. It means that we should do the pruning, cut this branch. Okay, therefore, we don't have to search for these 2 options. And we can cut this branch at this stage and backtrack to the previous node, which means we must undo. Okay, remove this queen and we are back here. Check the next one. It means to place the next queen in the third column. That works. That's okay. All right. So we keep moving. Keep moving to visit the next one. That is to place the third queen in the second column. Okay. It doesn't work. So cut this branch. Okay. We don't have to visit this one. Cut it here and undo. So recover the board and we are here, back here. Next, let's try to place the third queen in the fourth column. Still not working. So cut this branch, undo, and backtrack to this node. And at this moment, we see that this node is dead because we have no other possible ways to go. All right, so backtrack again, which means undo this one and we're back here. All right, try the next one. Place the next queen, the second queen, in the fourth row. So we're here. Next, place the third one in the second row. Okay, that's fine. And finally, place the last one in the third column. Well, that violates the rule. It means that this one should be cut. Undo this one. And we'll backtrack to the previous node, and this node is dead. Alright, so cut this one and undo. Back here, try the other option. Let's try to place the third one in the third column. It doesn't work. So cut this one and backtrack. Alright, now this node is again a dead node. So cut this one, undo, and we're back at node 2. Now this node is dead because it has no other way to go. Right, so cut this one and undo, and we're back to the root. Alright, let's start all over again. Let's try to move along the second branch, which means to place the first queen in the second column. And this node is alive, so we move on. Continue to place the second queen in the first column. It doesn't work. So cut, undo. Try the next one. So place the second one in the third column. It doesn't work. Cut and undo. Now we have one last option to go. So place it in the fourth column. That works. Alright, so we're at this node and it's alive. So let's try to place the third one in the first column. It's okay. And finally, place the last one in the third column. So, ta-da! We finally obtain a solution. So you see that the reason we call backtracking a smart searching is that before we obtain this solution, we have visited that many nodes, but not all of them. Not all of them. So these are the nodes that we never touched. Therefore, the time is saved. All right. Notice that when you really write a program, no tree is actually constructed. The game tree is just an abstract concept. So never ever construct a tree in your program. Why not? Think about the time taken to construct this tree. It's going to be the same as an exhaustive search, right? Because you have to create each node at least once. So what's the difference between constructing a tree and do an exhaustive search? It's even worse, right? So this game tree is merely a way to show you how it works. And remember, there must be no tree in your program.